So just after having detailed information regarding expression for the torque or moment of force when electric dipole is placed in a uniform electric field. And now we are going to deal with another expression for electric dipole. We can say energy associated with electric dipole when placed in an external uniform electric field. Or in another language, it can be said that work done by electric dipole when placed in an electric field. So let us see in the figure. This is a electric dipole. This is an electric dipole with negative charge located at A, and positive charge is located at B. And O is the center of dipole. An electric field is directed along x-axis as field lines are equally spaced, so we can say that electric field is uniform. Right now, at present, electric dipole axis makes an angle theta with the electric field, makes an angle theta with the electric field. So this electric dipole will have a tendency to rotate about this point in clockwise sense due to couple of force, one force acting in this direction minus QE and plus QE acting in this. So this will rotate, will have tendency to rotate. So one has to hold up in this situation. As soon as it is released from this situation, it will align parallel to electric field. So it cannot live on its own at this orientation if one does not hold it. It will automatically becomes parallel to electric field because it has tendency to become aligned with the direction of electric field in order to achieve a stable orientation. So far in the morning session, we have derived expression for electric dipole, expression for moment of force or torque when dipole is placed in uniform electric field, and expression of that torque was given by tau equal to P cross E or PE sine theta, tau equal to PE sine theta and gamma. Now here we see that at this orientation, this electric dipole will experience a moment of force or torque that will be given as tau equal to Pe sine theta. So if we displace this torque through a small angle d theta, then we have to do work, because as we displace this dipole just beyond theta through a small angle d theta, then we have to do some work against electric field, and that work done will be stored as electrical energy in the electric dipole. So let us check out. As dipole experience a torque Pe sine theta and angular displacement is d theta, therefore work done, elementary work done or differential amount of work done is given as Pe sine theta into d theta. And now we integrate, because theta will change and everything will remain same, but theta will change. As P and E, P is a dipole moment and E is the electric field. Both are uniform and constant, so it can be taken out of the integral sign. Now, a variable thing is that theta, angle will change. So it will, suppose it will change from theta 1 position to theta 2. So lower limit will be theta 1 and upper limit will be theta 2. And work done will be changed from 0 level to W. Because before orientation, work done is 0, and after that, work done will be W. So after integration, we have dW, integration of dW equal to W, and integration of sine theta is minus cos theta. So taking minus outside, and now take the upper limit and minus lower limit, and you get this situation. This is the expression for work done. This is general expression for work done. Now, we restrict the situation. If we take initial orientation of dipole is at an angle theta 1 equal to 0, and final orientation of dipole is theta 2 equal to theta, then we place theta 1 equal to 0, then cos 0 equal to 1. So, and theta 2 equal to theta, so cos theta, this becomes cos theta. So our expression will be W equal to PE into 1 minus cos theta. Now, remember, again, if we take another situation, if theta 1 is equal to 90 degree, say this dipole is taken to this position here, point B is taken to this position here, and A will come to this position, then angle becomes 90 degree. So at this 90 degree angle, when dipole is released, dipole will on its own becomes parallel to electric field and making angle theta equal to 0. So if we take initial position at 90 degree, so point B is here, then angle becomes 90 degree, then theta 1 equal to 90 degree. In that situation, cos 90 equal to 0, and then W equal to PE cos minus cos theta, because theta 1 is 90 degree and theta 2 equal to theta, then in that situation we will have W equal to PE cos 90 minus cos theta. Cos 90 becomes 0, so we get minus PE cos theta. So minus PE cos theta can be expressed as negative of dot product of electric field and dipole moment. That is P dot E, minus P dot E, it can be expressed as. And this amount of work done is stored as electrical energy in the dipole. Okay, so this was the two expression associated with the electric dipole when placed in uniform electric field. Okay, now next topic is Gauss law. So far, सभी लोग अपने मोबाइल को म्यूट कर लीजिए. So far, electric flux has already been discussed. So now we are going to deal with another fundamental law of physics, which relates electric charge and electric flux together. So now try to understand, we have to know about Gauss law. What do you mean by Gauss law? Gauss law states that electric flux linked with a closed surface is just equal to 1 by epsilon naught times of charge enclosed by the surface. So, and mathematically, flux is denoted by phi, and according to Gauss law, net flux enclosed by the surface is just equal to Q by epsilon naught. A net flux through the surface is just equal to total amount of charge enclosed by the surface and divided by epsilon naught. So let us prove this statement. Now consider a charge Q is situated at this location at the center and enclosed in a Gaussian sphere of radius r. Gaussian sphere is an imaginary sphere we draw in such a way that a sphere will pass through the point where electric field is to be measured or to be determined. So charge, this much charge is enclosed by this sphere. You see, how much charge is enclosed by this sphere? Q. Total charge enclosed by this sphere is Q. And this sphere is not a real sphere, it is an imaginary sphere. So just like our atmosphere has a spherical shape, but it is not a real sphere. So try to understand. A radius of this sphere is r. Let a small area ds here This is the small area ds taken as, and electric field line is originating from this charge will pass through this area. Electric field line and area vector will be parallel to each other. So angle between electric field line and area vector is 0. Therefore, in order to determine electric flux, we just take a scalar product of electric field vector and area vector. So let a small area ds at any point on a sphere whose direction is along the direction of electric field intensity, because area vector is always directed in the direction perpendicular to the area. So here electric field is also perpendicular to this much area, and so area vector will be directed along this electric field. So angle between area vector and electric field is 0. And hence the electric flux linked with this small area d phi is given as vector E dot vector ds. E is electric field and ds is elementary area vector. E is electric field at this location only, at distance r. So remember, so this is the electric flux linked with this small area. Now we have to find out entire electric flux linked with the whole surface of this sphere. So we integrate this differential flux, and remember here d phi equal to E dot ds, because angle between electric field and area vector is 0. So d phi equal to E ds cos theta. Here theta equal to 0. Therefore d phi equal to E ds cos 0, and hence d phi equal to E into ds. Now putting value of electric field at this location. So as we are dealing with this point on this point, so this point is situated at a distance r from this charge. So electric field at this surface, elementary surface, will be k q upon r square. Here q by 4 pi epsilon naught r square. 1 by 4 pi epsilon naught को हम q k कह सकते हैं, लेकिन हम उसको पूरे को प्लेस कर दिया. Q by 4 pi epsilon naught r square, where q is total charge enclosed by the sphere into ds. Now integrating along closed surface in order to have electric flux through the entire surface, Gaussian surface. This is imaginary surface which is called Gaussian surface. So integration, यहाँ सर्किल मैंने बता दिया था पहले ही कि ये इंडिकेट करता है कि through the closed surface, those closed surface which encloses the charge. So d phi equal to ds, क्योंकि वेरिएबल क्वांटिटी केवल ds यहाँ पर है, बाकी ये सभी तो कांस्टेंट ही है, बिकॉज जब तक स्फीयर हमने ले लिया है तो उसका रेडियस फिक्स रहेगा. इसलिए आफ्टर इंटीग्रेशन d phi becomes phi and ds becomes, क्योंकि स्फीयर है तो स्फीयर का टोटल सरफेस एरिया क्या हो जाएगा 4 pi r square. Therefore q by 4 pi epsilon naught r square into 4 pi r square minus 0. 0 इसलिए लिया गया क्योंकि स्टार्टिंग सरफेस एरिया हम करेंगे 0 से 4 pi r तक, तो अपर लिमिट हो जाएगा 4 pi r. इसलिए फाई अभी एक 4 pi r square कट गया, सिर्फ बच गया हमें q by epsilon naught. Hence Gauss law is proved. Gauss law यही कहता है कि total electric flux linked through a surface that encloses net amount of charge is just equal to 1 by epsilon naught times the total charge enclosed by the surface. So this has been proved. And next thing is that try to understand ये गॉस लॉ का स्टेटमेंट और गॉस लॉ का प्रूफ हो गया. अब हमें डिस्कस करना है गॉस लॉ का एप्लीकेशन. तो एप्लीकेशन को हमको लगता है कि नेक्स्ट डे डिस्कस करेंगे, एप्लीकेशन ऑफ गॉस लॉ. ठीक है, आज इतना ही छोड़ देते हैं. हेलो.